Welcome back to Advent of Code 2025, day 8. So we're going back and completing the backlog, so just 8 to go. Hopefully we can get that done today. And tomorrow we can finish on time as we can. I could see that the diagram, we've got the paper rolls there with the forklifts. We've got the wires. The last one was what, a cinema? What is this thing? Oh, that's what we just did, the cinema one. Alright, 8, let's go. Playground, equipped with the new understanding of teleporter maintenance. You confidently step onto the repaired teleporter pad. You rematerialize on an unfamiliar teleporter pad and find yourself in a vast underground space which contains a giant playground. Across the playground, a group of elves are working on setting up an ambitious Christmas decoration project. Through careful rigging, they have suspended a large number of small electrical junction boxes. Cool. Oh, that is a short wiki. Oh, yeah, it is pretty short. Not a lot to say about junction boxes. Their plan is to connect the junction boxes with long strings of lights. Most of the junction boxes don't provide electricity. However, when two junction boxes are connected by a string of lights, electricity can pass between those junction boxes. This is going to be a flood fill. The elves are trying to figure out which junction boxes to connect so that electricity can reach every junction box. Oh, it's strongly connected components, something. They even have a list of all the junction boxes' positions in 3D space. In 3D space? To save on string lights, the elves would like to focus on connecting pairs of junction boxes that are close together as possible, according to straight line distance. In this example, the two junction boxes which are closest together are this and this. My nightmare. What 3D space? There's an old maths joke. Visualizing things in 3D is easy. Just visualize it in n dimensions and then set n equals 3. By connecting these two junction boxes together, because electricity can flow between them, they become part of the same circuit. After connecting them, there is a single circuit which contains two junction boxes, and the remaining 18 junction boxes remain in their own individual circuits. Oh, this is neither of the things I mentioned. This is minimum span tree, isn't it? This is Kruskull's algorithm for minimum span tree. Kruskull's or Prim's, one of the two. They're not only describing the outcome, they're describing the actual algorithm to follow. Now, the two junction boxes which are closest together but aren't already directly connected are those. Oh. Okay. Right, so I think Prim's algorithm is the one where you build up one connected tree and you always add the closest node to that tree by minimum distance, so that you're always continually building up one tree. Kruskull's algorithm, I can't remember what that one does. But what they're describing is one where you always take the smallest two, regardless of whether they're in the same connected component or not. And then so you probably want like union find algorithm or something. We can look this all up in a minute. The next two junction boxes to connect are... yeah, okay. Because these two junction boxes are already in the same circuit, nothing happens. This process continues for a while, and the elves are concerned that they don't have enough extension cables for all these circuits. They would like to know how big the circuits will be. After making the 10 shortest connections, there are 11 circuits. One circuit which contains 5 junction boxes. Oh, interesting. Okay, we're not making a minimum spanning tree at all. This is... I've mentioned like a million different algorithms at this point. This is union find. I think that's what this is. Union something. So once you've done 10 connections, then you have a bunch of circuits. You take the largest 3. Okay. Alright. Hello, Smab UK. Just managing to catch up, hopefully. I'll be caught up by the end of this stream. Looks alright. I think this is, let me look up this thing that I mentioned. Union find. Union find data structure. I mean, this is one way of doing it, I guess. Where you have a representative of every set. And whenever you union 2 sets, you choose one of the 2 representatives to become the new representative of the joined set. And every element of each set is remapped to that representative. But you can also do it without having to remap everything. You can just go to build a tree where it's pointing back to the representative via some tree. But I mean, its input is small enough. We could just do kind of like a full thing. So okay. I ended up using a heap for part 2 that took 5 minutes to run. Alright. Guessing for part 2 they might extend it from the top 10 to like the whole map or something, I don't know. I'm actually caught up, but given the last 2 days, I dread tomorrow. I mean, traditionally, day 25 has generally been okay, but of course, it's day 12. It's not Christmas Day. We don't have families to be worrying about. So yeah, it could well be a tough one. We don't have families to be avoiding because we're busy coding. Okay. Alright. Alright, so let's just pause these inputs. X, Y, Z equals split on the comma. And these are junctions. Call them junctions. So we'll need a helper method. Dist between junction 1 and junction 2. Is it Euclidean? Yeah, it probably would be. According to the straight line distance. That's, yeah, Euclidean distance. Okay, so we'll do the square distance. return sum of J1 K minus J2 K for K in range 3. Okay. I'll just move this stuff down here. Okay, so for part 1, so how are we doing this? I guess we want a data. Let's create a class called a union. The only thing it needs is a representative. Let's call it a rep. We can define add you add you would be self.members dot pet you. So we create a union for each individual point. Let's just put them all in a list somewhere. Unions equals that. For P in, or for, yeah, P in junctions. Let's create a new union centered on P. We also need a way of knowing for any given point which union it belongs to. So just create a map. And union map P equals, okay, so we need to create the U. Okay, so now we've got our unions. All right, so we now have partitioned the space of points into a bunch of unions. Each one has one member. Actually, strictly speaking, we should. This should be. Let's do this properly. This should be, what's the word? can't remember the word for when it doesn't change. Well, it should be that. So should not do this. We should actually have static. No, not static. Union.union with self.other, and that will return a new union, which it takes both. So when we create a union, we don't do that, or at least we can, I suppose. Alright, so we say, we give it a list of members, that's what we do. An iterable of members. Alright. We set the members to be that. And the moment we've created the union, we say for M in members union map M equals self. All right, so we're pointing back to this class. All right, so that handles that. We don't need to do this down here, and we don't do that. When we want to create a new union, where we union two of these things, we say new members equals we're gonna use lists or sets. Should be sets, I suppose. New self dot members union with other dot members, and then return union of new members. Okay. And down here, all we do is just say do that. All right, is that everything that I wanted to do so far? Let's print this and see what it looks like. Okay. And because we've done this, we want to make this frozen, don't we? Frozen set? Is that the word you use? Let me look this up again. But does that mean we can't use init? Yeah, immutable. That's the word I was looking for. Immutable. No. Not frozen set. Frozen equals true. Frozen. How do we do it? I don't remember that. Data class frozen equals true. That's how we do it. Data class frozen equals true. There we go. So we never change. Oh, that means we can't do init. So we have to say members, which is a set. We have to do... Does that work? Let's try union map then and see if that works. It doesn't have members at the time that you call that. How? I don't remember how to... I'm trying to be overly software engineering this to make these everything like proper and immutable, but this is all unnecessary. But it's good practice. I don't remember. You can't really do init when you've made it a data class, can you? This is members. I don't remember how to use data classes at all. Python data class. Laptop product. Oh, you just list its parameters like that. Okay. So why wouldn't this work? Why is that an unexpected argument? Members. Oh, it just doesn't like me having this at all. Oh. But... Okay, go back. We have to make this non-immutable, I guess. I don't know. I don't remember how to do this. There's a way. I think you have to override the frozen for specifically the things you want to alter. Alright, well this was working. Print union map. Okay. Alright. This was unnecessarily complex, but I mean this is like a proper class and everything. The important thing is we've mapped a bunch of things to representatives, and now we have a way of tying things together, knowing in constant time basically if a given element already has a union. Well, it always does, but we know which union it has and whether it's the same one, because every element of a union always has the same representative. That's forced by we're not pointing to a representative anymore. We're pointing to the class instance itself. I guess that's fine. The class instance has a pointer address, which is unique. So if both are pointing to the same union, that should be okay. Yeah. Now, the standard way, the classical way, is to choose one element of the set to be representative. But I suppose you can do it this way. I hope it works the way I think it does. Let's test it. So, let's just carry on writing solving the problem so I get that all written down. Alright, so we've got these. Now what? What was the question? Okay, so for range 10, that's what they said. 10 times we do this. We want to take the closest pair . So do we just have to take all pairs and just put them into one gigantic list and sort them? Yeah, I guess so. How about the other? Okay, that's fine. It's gonna be big, but all pairs. Whoa, what am I typing it here for? So all pairs equals for P in for IP in enumerate junctions for JQ in enumerate junctions starting from I plus 1. All pairs dot append. So we just want to put a tuple where the first parameter is the distance. It's going to be dist between P and Q. And then yeah, we don't need to do that. Just put Q in there. And then do all pairs dot sort. Key equals lambda. Pair dist 2 between pair 0 and pair 1. Let's just have a look at what we got. So the first pair should be close together. Take a while because it's like a million or something, but right. Oh, it's gonna be too many. Alright, print all pairs. Those are the ones we'll be using. So 9707, 97073. These are identical. Damn it, what? They aren't duplicates, are they? Oh, what have I done? What? How did this happen? Let me just make sure there's no duplicates in here. Print length of junctions followed by length of set of junctions. 1,000 of 1,000. There's no duplicates. What's wrong with my enumerate? Is this not how you use enumerate? look up the documentation for this. Oh, is that not how the enumerate thing works? What? So, oh, the start parameter for enumerate isn't saying where to start on a list. It's saying what index to start at. How do you? Oh, screw it. We'll just do it the classic way. For I in range, that's fine. That line's fine. For J, I could have sworn there's. I don't want to do junctions sliced because that's just takes the whole of junctions and creates a new list every time. All right, we'll just do this. For J in range, I plus 1 length of junctions. I could have sworn there was a clean way of doing that. It probably is. Alright, check that. Okay, so these two close together, and then these two. Yeah, I guess. Okay, so far so good. Okay, so for P, Q in all pairs up to 10. We take P and we take Q and see if they belong to the same union. So if they do belong to the same union, you don't do anything, do you? But does that mean you have to skip to the next one? Let me read the instructions again. The next two junction boxes are blah blah blah. Because these two junction boxes were already in the same circuit, nothing happens. After making the 10 shortest connections. So they're saying specifically each time you make a connection. So we specifically have to make 10 new connections. Okay. So slightly different from what I've written here. So Q keen walkers. So connections equals 0. Okay, so if so union map P is the same as union map Q. Why have I... Okay, this unions list is not... There's no reason to have this. Get rid of that. It just has to exist in memory. And is pointed to by the element itself. Just do that. Okay. So if they're the same, then we continue. Otherwise, we want to combine them, right? So we want to do this dot union that. And that just creates the new union in memory. The old thing might get garbage collected, or maybe not. Doesn't matter. Union. Okay. Then what? Oh, we do need to keep track of the unions, though. Because afterwards it says, what do you get if you multiply together the sizes of 3 largest circuits? So either we just now range through all the... I suppose we can do that. 3 largest sizes. Okay, fine. I guess we just do another for loop. So we say, now, if we want to find all the unions and how big they are, then do this. Menu list. I'm going to now find all the unions that exist for P in junctions. It's gonna have to be a set, isn't it? Unions dot add P, then unions equals, let's just make it a list of sorted unions where key equals lambda u maps to the length of u dot members. So it's sorted by how big they are. Reversed. And then print did they say multiply? Yeah. Let me check this again. Multiply the sizes of the 3 largest, okay. Okay, this ended up way more complicated than I thought it would. Just the way I did it, I guess, but I think it's kind of prepared for what they might throw at us in part 2, but we'll see. I don't know if it's right, though. 0, 1, 2. Unions has only got one thing in it. What? List sorted unions. What have we got here? Don't tell me everything's just... Oh, it is. We went through the entire list of pairs and connected everything together. Connections plus equal 1. If connections is 10, break. Alright. Eight. Wait, how many times did they say to do it? It can't be that small. 5, 4. So for the example, it was 5, 4, and 2, and that multiplies together to get 40. Oh. The example, they decided to connect together 10 things. We actually want to connect the 1,000 pairs which are closest together. We actually increase it to 1,000. Alright, let's check the example case before a rare case where I actually test the example before the real thing. So we should expect to get 40. 50? How did we get 50? Alright, well that's not good. Close, but also way off. Size of... Okay, we need to find what the largest circuits are. Print unions. Or print... U dot members for U in unions. Print. 5, 5, 2, 2, 1, 1, 1, 1, 1, 1. 2, 1, 1, 1, 1. It should be 5, 4, 2. Okay. Closest together but aren't already directly connected. So we don't take pairs which are already connected. Okay. Okay. Let's just print out step by step which ones we're doing. So it should be... How many it should be? There should be 11 circuits, 1 5, 1 4, 2 2s, and 7 1s. We got 2 5s, 2 2s, and 6 1s. Alright, fine. It's probably easily fixed. Let's... Wait, so for the example, they want 10 connections, right? Yeah. Okay. Okay, fine. Let's go step by step. So we want to print P and Q. Just check that we're doing the right P's and Q's. So 162.817.812 with 425.690.689, is that right? Yes. 425.690.689. So they become the same circuit. So we've got a okay. Then the next one is 162.817.812 with 431.825.988. 431.825.988, correct. And then next two junction boxes to connector. So it'll be 906.360.560. Yes. With 805.96715. Yeah. Alright, we're probably getting the pairs in the correct order. Then 431.825.988. Yeah. 425.690. And it says, and nothing happens in that case. Okay. After making the 10 shortest connections. Wait, do they actually mean... making the 10 shortest connections? So do they mean specifically 10 connections are created? So if we skip over something that doesn't contribute to the 10, it's not completely clear. Skipped counts? Wow. It's weird. Because they literally say the word make. The connection is made. So you would think that means, you know, you're actually making something, but you're skipping over it. Alright. I can try that. That's okay, so I mean, does that mean we just do this then? $40, there we go. Really? Okay, fine. I don't think that's worded correctly then. Like it used the word make. So that to me would imply that a connection is created where there wasn't one. So I would have said one for each actual new connection made, but all right. Let's test the big example then. Okay. But this has got to be 1,000. $72150. Correct. Fine. The elves are right. They definitely don't have enough extension cables. You'll need to keep connecting junction boxes together until they are all in one large circuit. Continuing the above example, the first connection which causes all of the junction boxes to form a single circuit is between the junction boxes at 216.146.977 and 117.168.530. The elves need to know how far those junction boxes are from the wall so they can pick the right extension cable. So we continue this process until they're all in the same circuit, i.e. the union size is 1,000, or length of junctions. Seems straightforward enough then. So we can maintain part 1 by just saying so let's say I PQ in enumerate all pairs. Okay, so we do this as we did before, but now we look at what's happened. So in the case of I equals 9, not 9. Okay, so let's say part 1 cap equals 1,000. So if I is part 1 cap, then we just do all this. Okay. So that's part 1. We continue doing that. So as soon as we've made a union, so we're here, and let's call it U. If length of U dot members equals length of junctions, then we everything should be in the same union, right? Should be all connected. The x coordinates, okay. Print. So the last two things we entered were P and Q. So print P times Q. Just the two x coordinates? Yeah. And break. Is that it? Alright, let's go. Oh, why did I change the answer to part 1? Oh, wait, did I? I did. Oh, God. What happened? Part 2 might be correct, but 999, you start at 0. Am I off by 1? If I is equal to Yeah, it should be -1, right? If I is equal to... Yeah. That's right. Okay. Wait, what? Does that need to be bracketed? Why am I not getting anything now? If I equals... Huh? Let's take this out for now. If I... $84175. -1. I'm so confused. What happened here? What? How many things are in all pairs? There should be loads. There shouldn't just be 1,000. Am I going mad? What? Why would this... Oh! Yeah, of course. This should be further up. Okay. Because it skipped over that, because that was a skip over, so it skipped over this logic. I think the 1,000 is just the total input line, so not something you need to keep in mind. Huh? No, it did specifically say 1,000 pairs. You actually have to cap it at 1,000. No, but that wasn't the problem. I think the problem was this logic was getting skipped over because of this continue. This logic should be up here. And we should not have -1 if we do that. We should have, we should actually go on 1,000. So 999 was the last thing we did. And then, before we do this logic here, because this actually skipped over that, we've done 1,000 iterations. Print part 1. Carry on doing this. But you do have to cap it at 1,000, I think, because there's more than 1,000 pairs. 72150, so yeah, that's still the correct answer for that. And part 2. Yay! We're all caught up. That was a pretty good problem. And I mean, I did it in a pretty robust way. I think you don't really need to go to the trouble of making like a union data structure like that, but it certainly helped for part 2. I mean, the classic way is usually to have a representative element of each thing. Basically an ID number It's the same concept. It's just I was just using the pointer of the union class itself. But in classical algorithm theory, you pretend pointers don't exist. But I mean, there's different ways you can do it. So I was doing like a full linear time union, where when you create the new union, the amount of time you spend creating it is the sum of the sizes of the two unions you add. Whereas, like, if you're being more efficient, you would only add the smaller union to the bigger one, so you're always using the smaller one, which would reduce the amount of work you're doing. And furthermore, you can optimize the union method by instead of just pointing everything to I don't know. There's different ways you can improve it, like some of which will mean you have a quicker time for computing the union, but you're sacrificing the amount of time used for looking up the representative or making queries. The way I did it makes those queries really fast, but it means the union is slow. It's just a full rebuild of the union every time. Now, I mentioned Kruskalls before. I forget what prims and Kruskalls are, what the difference is, or whether they're related here. Is the end result here going to be the minimum spanning tree? It would, wouldn't it? And that's the whole reason, that's one of the motivations for having union data structures in the first place. One of the early algorithms you learn is Kruskalls algorithm. Let's look this up. So it's a greedy algorithm used for finding a minimum spanning tree. Sort all edges. Initialize a forest. So at any given time you have a bunch of trees which are not connected. Yeah, this is literally Kruskalls, but step by step, so we didn't even have to know Kruskalls, we just had to do the steps. But the important thing about Kruskalls is that if you want it to run reasonably fast, you should be using a disjoint set data structure. That's basically the union thing I said. That's the correct term, I guess, disjoint set. And like my time was probably quadratic, but you could make it faster by using trees, I guess, to store the the mapping. I just held a list of hash maps, merged the maps as needed. Absolutely not optimal, but they're very straightforward. Yeah, I mean, at the end of the day, it's probably not much different in runtime because I was just doing a linear sweep anyway. But I never use Kruskalls if I'm doing an MST. I always use prims because it's just easier to code when you don't have a disjoint set data structure at hand. They're one of the, I think it's the first algorithm I ever learned before I even knew what an algorithm was. And this was back in school when I was a kid, and I took a course called, in A-levels, I took a course called, what was it called? Optimization or control, optimization and control, something. And I didn't understand any of it, but we were taught how to do prims and Kruskalls by drawing little boxes and writing down pointers, and I thought it was really complicated, and We were taught prims and Kruskal's and how to do it for a diagram, like on paper. We didn't use computers. It was all pen and paper. And yeah, that's the first algorithm I ever learned. Oh, we were also taught Dijkstra's after that. But it was a bit early to be learning that stuff. It's it's better to start learning data structures, I think, before you start worrying about algorithms. But that was just like an optional A-level module. Tomorrow's problems runtime ends up pushing my AOC total over 500 milliseconds. All right. The key difference is that Kruskal's algorithm is generally better for sparse graphs, while Prim's algorithm is often preferred for dense graphs. Interesting. Yeah. Most graphs you work with are sparse, generally, because dense graphs are kind of... being dense just makes them like it takes a lot of time to do anything with them anyway, and sparse graphs represent a lot of real-time data, real-life data. For example, friends networks like on Facebook or something, or physical distance networks where there's only so many things that can be close to you. But prims is easier to code, so I would always go with prims. So prims, if I remember correctly, prims, you always just build one big tree, and then you find whichever node is closest to your tree, but still disconnected, you then add that one to your tree, and so on. Yeah, that's pretty easy, and I guess you can use a priority queue or something for that, or... Not even that. Oh! I just saw something. Where was it? There, edXL A-level further maths. That's the exact module I took. This is how they teach it to kids. Who've like never done any programming or anything. But now they actually have an A-level called computer science. They didn't have that when I was in school. I totally would have done it. Alright. Okay. Cool. We're all caught up. I didn't know if I would be, but I am. So tomorrow we can actually do day 12 on time. I will be sure to wake up for that. Hang on. And we'll see if anyone's still doing Advent of Code right now. We could maybe raid them. Alright. Alright, it feels way better now that I don't have a backlog of problems.
That is very true.
I didn't have a look at the leaderboards. Well, let's just quickly look at them. I don't like this ordering. Just, how do I change it? Stars. Stars ordering. I would say whoever has more stars should be at the top, and then you sort by the time that it was done. Pretty good. So that was actually a pretty high success rate as well. I guess that's partly because part one involved a bit of work, and part two is just an easy extension over part one. So when you have situations like that, you get a high proportion of gold to silver, but overall a low completion rate. But yeah. But if you do manage to do part one, then you should be able to get to part two pretty easily. Is this Polish? All right. Shumara is doing it in.
I think we look at how it's we have a space that separates the two.
Language is that? Anyway, I'll just rate them. And see you tomorrow for the finale. Bye bye.